Compounds. All right, let's move on. We're on about page 54, 55, as I said. We will try to be as productive as we can today with the time we have. This week is revival week, so we're going to have short days. We'll do what we can each of those days. Chapel schedule for the next 3 days. So here we go. What is a compound? It's a blue definition in your book on page 54 that a compound, those are substances that can be decomposed into elements by chemical means. It can be decomposed. That all matter comes in two basic forms. They're either in the form of elements or in the form of compounds. Remember I said I can go ahead and build a big dramatic structure now, but let's pretend it wouldn't happen this way in real life, but this is a compound, right? This is one thing. It's made up of blues, reds, yellows, and greens. And if we go by the analogy I had before, here's a compound. It's made up of multiple pieces. It's made up of more than one kind of element, right? Here we've got blue elements, red elements, yellow elements, and green elements. If I take this large structure and I break it down, and I can break it down into different elements, it's a compound. So everything exists as either an element, meaning it, at the atomic level, is the only structure. Each Lego is individual, but it's, or if you have a mass of it, they're all the same kind. They're all greens, they're all yellows, they're all reds, they're all blues. If I take those pieces and build it back up again, I now have a compound. And that's why I have this two ways of viewing it. Either elements combine, you can think of it as construction. It's called a formation reaction. I can take the pieces of different kinds of elements and stick them together to make a structure. That's a compound. Or think of it in the inverse. I can take something that's made up of a bunch of different things, and when I break it down into its fundamental building blocks, blues, reds, yellows, now I've broken it down into elements. So either a compound, you can think of it as I take pieces and I build it up. I take individual elements and I combine them to form a compound. Or think of it the other way. I take a compound and I decompose it and I break it down into individual elements. So any questions on that? That everything that we have is either an element or compound, or you can get even more detailed than that. It's either elements, compounds, or mixtures of elements and compounds. But those are the basics. Either it's pure building block, or it's a combination of different kinds of building blocks. It's one element, or it's multiple elements. That's a compound. So if I have something that I can break down into smaller blocks that are known as elements, then it's a compound. If I have something that can't be broken down anymore, it's an element. Okay? Pretty basic concept? We good to go? All right, go ahead and move on then. Well, we get to compounds, and this is kind of a neat thing. We use, not because I'm Mr. Baker, but I like to use baking analogies in here. It doesn't fit perfectly, so I get that out of the way. I do use baker's dozen every now and then, but it's not because I'm Baker. It just works out that way. So we get into this idea, and it's also on page 54, the law of definite proportions. The proportion of elements in any compound is always the same. I like to use the analogy of a recipe here. In chemistry, we're always trying to get to the perfect recipe. The perfect recipe for something. But here's the difference. If you are in the kitchen and you mess up the recipe for muffins, okay? You've got the perfect grandma's muffin recipe. This is the perfect recipe. If you follow the recipe, you get the perfect muffin. You love it. It's awesome. Everybody wants it, right? Wants them. If you mess up the recipe, you still get muffins, don't you? They may taste pretty nasty. They may be chalky. They may have too much baking soda, baking powder. Your proportions are off. You'll still get muffins, but they won't be quite the same. It's different in chemistry. In chemistry, if you mix the same elements and you create compounds, and you add more of something or less of something, it doesn't change what you produce. It changes what you have left over. So think of it this way. If you have a recipe for a cake, and that cake calls for 3 eggs, but when you make that cake, you put in 4 eggs. Now in baking, you would get a cake that comes out, you taste and go, it's a little bit off. I may not know what it is. But in chemistry, the analogy would be this. I make the cake, I put in one too many eggs, I bake the cake. When I look at the cake at the end, I have a cake and an egg. Why? Because that extra egg doesn't get folded in and become, it doesn't change what you're producing because you've got too much of something or too little of something. What it does is it makes the perfect recipe and then it leaves the leftovers behind. All right? So that analogy of I get the perfect recipe for a cake, I put in one too many eggs, and when I pull it out of my Easy Bake Oven, I have a cake and an egg. And what does that tell me? I put in one too many eggs. So if I go back and look at it, if I followed the recipe perfectly, but I have one extra egg, I have a cake and an egg at the end, what am I going to do next time I make the recipe? Put in one less egg. Because what I'm trying to do is create a recipe such that when I put all the ingredients together, what comes out of the Easy Bake Oven is exactly what I'm trying to make with nothing extra left over. Because if there's anything left over, think of it as being this little pile on top of the cake. Hey, you know what? Too much salt. How do you know? There's a pile of salt on top of the cake. A little bit too much sugar. How do you know? Here's the deal. You put in a little bit too less sugar, what's going to happen? You're going to get less of a cake and have everything else left over. You're going to have a little bit of egg left over. You're going to have a little bit of, you're going to have a little bit of everything left over because it's going to make the perfect recipe. And if you're too short on something, it'll make less of the perfect recipe than you planned, and you'll have everything else left over. And if you put too much of one thing in, you're going to make the perfect cake and have a little bit of that one thing left over. See how it works? So this law of definite proportions, it's saying that the proportion of elements in any compound is always the same. It's always going to be exactly the same. And Proust figured this out. He said that when they combine together to form compounds, they're always combining in the same proportions. Well, an easy example of this that we're all familiar with is water. What is the chemical formula for water? H2O. Before chemistry class, you knew H2O was water. Dihydroxide. We don't call it dihydroxide. That's its chemical name. We use the common name, water. Dihydro, two hydrogens, monoxide, one oxide, dihydromonoxide, usually just dihydroxide. Okay, so we all would say, okay, hopefully it makes sense to you that I need two hydrogens for every one water. That's when you break it down to the individual atom. Two hydrogens, one oxygen, that makes water. What Proust did, and this is long before we broke it down to that degree, he said, hey, you know what? I know that whenever I make water, I've got to combine 8 grams of oxygen for every gram of hydrogen. So it's not like me coming to you and say, okay, you need 37 salt crystals for every 158 sugar crystals when you make your cake recipe. And you're like, whoa, Mr. Baker, you don't expect to count out every crystal, do you? Okay, let's generalize that. Let's take the mass of it. Let's take a certain mass of sugar and a certain mass of salt and a certain mass of flour to make the cake. Okay, that's more reasonable for us, rather than counting each little grain of flour, each little grain of salt. Proust came up and said, well, wait a minute. In this analogy, every time I make water, it takes 8 grams of oxygen and 1 gram of hydrogen. And if I have too much hydrogen, I make water and I have hydrogen left over. If I have too much oxygen, I make water and then I have some oxygen left over. See? So if we know that water, when I make water for every 8 grams of oxygen, I have 1 gram of hydrogen. If I were to mix 8 grams of oxygen with 1 gram of hydrogen, how much water would I make? How many grams of water would I make? Does anybody know? Have you all heard of this concept known as the law of mass conservation? That the mass of my reactants has to equal the mass of my products? What are the mass of my reactants? 8 grams and 1 gram. Okay, 8 plus 1 is, fill in the blank. 8 plus 1 is 9. So if I combine 8 grams of oxygen and 1 gram of hydrogen to make water, I'm going to get 9 grams of water. How do you know that? I've got 8 grams to start with and 1 gram to start with. That's 9 grams to start with. I've got to have 9 grams to end with because I can't make or destroy anything. I can just rearrange it. Okay? So by extension, if I have 80 grams of oxygen, to make the perfect recipe, how many grams of hydrogen do I need? If 8 8 oxygen and 1 hydrogen is the mixture, then 80 oxygen requires 10 hydrogen. How do I know? Well, 80 is 10 times this, right? 10 times 8 is 80. So 10 times 1 is 10. So if I combine 80 and 10, how many grams of water am I making? 90 grams of water. How do I know? Well, first, 80 and 10 is 90. Second, think of it this way. When I use up 80 grams of oxygen, do you see that I'm making 8 batches of water? Like if you made your cake or cupcake recipe and you had a recipe for a dozen, and I said, okay, if you have 3 eggs for a dozen, how many eggs do you need for 2 dozen? You'd be 6. How do you know? Because I made 2 batches, right? So whatever it is for 1 batch, I need 2 of them. Here, if I know the recipe that uses 8 grams, and I want to make, and I use 80 grams, I'm making 10 batches. 10 batches of oxygen. Well, I'm going to need 10 batches worth of hydrogen, so 10 times 1 is 10. And I'm going to make 10 batches worth of water, which I originally made 9, so now I'm making 90. It's a 10 batches of water, using that analogy of baking, okay? So, the law of definite proportions, and I'll go back to this repeatedly, but you need to be able to understand how to come up with the perfect recipe. In the case of water, it's 2 hydrogen atoms and 1 oxygen atom makes 1 water atom, H2O. And if I have 8 and 1 for the mass, if I use 80, I need 10, and it makes 90. So on figure 2.3 on page 55, we take these same ideas and we just kind of make it a little harder, but same concept. Let's just build this up a little bit more. In figure 10.3, from left to right, you see that there's 10 grams of sodium and 10 grams of chlorine that makes 16.5 grams of table salt, sodium chloride, and 3.5 grams of leftover sodium. Page 55, figure 2.3. So 10 grams of sodium, Na, natrium, okay, that's the chemical symbol for sodium. 10 grams of sodium, 10 grams of chlorine makes 16.5 grams of sodium chloride, 1 sodium and 1 chlorine to make sodium chloride, this much, and 3.5 grams of sodium left over. I'm trying to get to what's known as the balanced reaction equation, the perfect recipe. What is the perfect recipe for sodium chloride? What would that be? Well, I want to drive you back to think about that perfect recipe for a cake. Let's say that sodium chloride is our cake. We're trying to make cake, right? I know that to make sodium chloride, it takes sodium and chlorine. I put this much in, and I make sodium chloride, and I've got sodium as my egg. Sodium is my extra that's left over. Now, I said before, if you made brownies or cake, you put it in, it came out, you had an egg on top, what would you do? Subtract 1 egg. For this recipe right here, we've got extra sodium. What are we going to do? Get rid of the extra sodium. Do you see that? I've got sodium and chlorine. These combine to make sodium chloride. But I got leftover stuff. And the leftover stuff I have is one of my ingredients. So if I want to get the perfect recipe, I need to reduce my ingredients by whatever was left over. Okay? Reduce my reactants, that's my ingredients, by whatever was left over that wasn't needed to make my perfect recipe. So there's too much sodium. Later we'll learn about this term called the limiting reactant. And the limiting reactant is whatever runs out. If we've got too much sodium, what ran out? What ingredient don't we see all by itself over there? There's sodium and there's chlorine. We see sodium by itself. Do we see any chlorine by itself? No, because here's the deal. If there was chlorine by itself, what would it make? The sodium and the chlorine would match and they make more of this. Something's going to run out. And this is referred to as the reaction engine. I'll call it the reaction engine. If you've got the pieces that are needed to make something, the reaction's going to make them. I've got 1 sodium and 1 chlorine. Boom, boom, there's 1 and 1. Boom, there's a sodium chloride. Sodium chlorine, boom, there's another one. It's an assembly line. Sodium chlorine, boom. They're going to make sodium and chlorine. Sodium and chlorine. Sodium chlorine. Making salt all day long. making sodium chloride, and then there's no more chlorine. If I don't have the chlorine, I'm not going to take sodium. I have nothing to match it to make sodium chloride. So I just leave whatever I have too much of, the excess. And the thing I run out of is the limiter. It limits my reaction. I can't make any more. Why? I ran out of an ingredient. What ingredient did I run out of? I ran out of chlorine. You see that? I ran out of chlorine, which means I've got extra sodium. So I can make, in here I see the formula for making this much sodium chloride. If I've got too much sodium, then I take that out of my initial, right? So what I actually need is, how much mass total do I have? Well, the total I have is used up by the part that I used to make sodium chloride, and whatever's left over. I want to find out what I actually used. So if I have 10 grams to start with, and I have 3.5 that's unused, how much did I actually use? 6.5 grams of sodium. Since I used up all the chlorine, I now know the perfect recipe for sodium chloride. If I take 6.5 grams of sodium chloride and 10 grams of chlorine, it'll make 16.5 grams of sodium chloride and nothing left over. It's my perfect recipe. Okay? It works from the law of mass conservation. 10 grams and 10 grams is 20 grams. But when I reduce this by 6.5, by getting rid of the extra, 6.5 grams and 10 grams is 16.5 grams. So right now we're not sitting here saying, I need 1 atom of sodium for every 1 atom of chlorine. That'll come later. Right now we're saying, for every 6.5 grams of sodium and every 10 grams of chlorine, I can make 16.5 grams of sodium chloride and have nothing left over. Okay? So basically what this top equation shows us, in the lab, I take 10 and 10 and I throw it together. Those are my 2 ingredients for this, trying to figure out a 2-ingredient cake, and my cake is sodium chloride. Here, throw them together. What comes out of the oven is 16.5 grams of sodium chloride and 3.5 grams of sodium sitting on top. I had too much sodium chloride. Let me get rid of the extra from my initial recipe, and that's shown here, and it works perfectly. No leftover chlorine, no leftover sodium. Everything goes into the reaction for sodium chloride. This is my perfect recipe according to mass. 6.5 grams of sodium, 10 grams of chlorine gives me 16.5 grams of sodium chloride. But the analogy goes on. Right now, what we've covered is on page 55. We flip over to page 56, and they say, well, wait a minute. Okay, so what happens here then? If I put, the chemist goes in and says, okay, but let me put 19.5 grams of sodium and 30 grams of chlorine in there and get 49.5 grams of sodium chloride. We see by law of mass conservation, 19.5 and 30 is 49.5, right? My mass is all accounted for. There's no extra. But look, here's why. If this is the perfect balanced recipe from before, if I have 19.5 grams, and in my perfect recipe, it was 6.5 grams, do you see that I've got a multiple of 3? And then 30 is what? It's 3 times 10. So if I've got 3 times this and 3 times this, what do you suspect I'm going to make? 3 times as much of that, right? So basically, this is the same thing as before. 6.5 plus 10 produces 16.5, but it's a triple batch. 3 times as much. You see, that's the law of that's the law of definite proportions. If you've got them in the right proportions, they will produce in the same proportion. If I've got 1 perfect recipe, 1 batch, or 2 batches, or 5 batches, or 10 batches, or 30 batches, or 60 batches, if I've got the perfect ratio of ingredients, it's going to produce my perfect product with nothing left over, which means nothing short. Everybody matches out perfectly to the recipe. So 3 times the reactants produces 3 times the products with nothing left over. Now they ask the next question. Okay, so what happens if I take 6.5 grams of sodium and 15 grams of chlorine? It says I'm going to produce 16.5 grams of sodium chloride, and what else? What else am I going to produce? You tell me. What's that?
Would it be extra chlorine?
Okay, remember, if 6.5, let me go back right here. I've got 6.5, the perfect recipe is 6.5 and 10 makes 16.5. I've got too much chlorine. I've got 5 grams too much chlorine, right? Because 6.5 and 10 makes 16.5. So it's going to produce 16.5 grams of sodium chloride and then 5 grams of chlorine left over. And in this case, I ran out of sodium first. The last time I ran out of chlorine first. And that just shows you the reaction stops once you run out of one of the ingredients. It makes it, it makes it, it makes it, it makes it, it makes it. Now, whoop, this bin is empty, everything stops. I can't make any more. So I've made the perfect recipe, however many batches worth, and then the excess is left behind. In this case, I ran out of sodium. I have the right amount of sodium and I have too much chlorine to make this much sodium chloride, so my leftover chlorine is left. If I want to make more sodium chloride, what do I have to do? I'm going to have to add more sodium. Because I've got chlorine. Think of me as the reaction engine. I've got a bin with chlorine still in it, but I don't have any sodium. You give me more sodium, I'll make more salt. But I got to wait to get more salt. Otherwise, I've got extra chlorine just sitting around waiting for sodium to match to it to make more sodium chloride. Okay. So that perfect recipe means that if you don't combine in the right proportions, some of the reactants will be left over in the products. And if we know the perfect recipe, we can predict how much we're going to need. We can predict, like if we're purchasing agent for a company, I know when my company is going to make a certain chemical, I can go out and figure out how much of the components I need to buy so that we can mix them together to make the right amount. I'm not buying too much of one thing, too little of another thing. I've got a customer that wants a certain amount of the compound. I can figure out, knowing the perfect recipe, how much of each of the components I need to have on hand to react to make that much product using the perfect recipe formula. The law of definite proportions. So let's go ahead and take a look at example 2.2. It's on page 56 and 57. Kind of run through it real quickly. It says a chemist reacts 15 grams of calcium with 15 grams of oxygen, and it makes 21 grams of a compound known as lime. Okay, I wrote lime up there. Along with the lime, there is also some leftover oxygen. Doesn't say how much, some. If the chemist wants to make 55 grams of lime and have no leftover oxygen or calcium, how much of each element should he use? So we're trying to find the perfect recipe, right? None left over, none of anything left over. We want to react it perfectly. And this is a good case. I'm a purchasing agent. How much do I have to give the chemist so he can make the right amount? So 15 grams of calcium and 15 grams of oxygen produces 21 grams of lime and some extra oxygen. First question to you, how much extra oxygen? If 15 and 15 makes 21 and something, what's the something?
9.
Based upon law of mass conservation. Basic math from the law of mass conservation. The mass of the reactants has to equal the mass of the products. So my perfect recipe, if I know this, is going to produce 9 grams of oxygen, right? What do I have too much of? What element do I have too much of? Oxygen. You see, I've got leftover oxygen at the end. I want no leftovers. So how do I change my recipe to have no leftover oxygen? Right, I'm going to subtract out my excess, my extra. I don't want any extra. I'm just trying to find out in proportion, for this much of one, I need this much of another, and it'll produce how much. So do you see, hopefully everyone, give me a bobble here. Do you see that when you combine 15 and 15 to produce 21 and 9, that you have too much oxygen? Okay. And to get rid of that, I need to subtract it out. I subtract the excess. So I had 9 grams too much, so I go back to my reaction, and I subtract the 9 grams out of my reactants, which means that now my perfect recipe is 15 grams of calcium, 6 grams of oxygen, produces 21 grams of lime. I can check it by going 15 and 6 is 21. Boom. True. It works. Law of mass conservation. The mass of my reactants equals the mass of my products. So this is my perfect recipe for lime. The question says, I want to make 55 grams of lime. How do I do it? What do I have the perfect recipe for? 21 grams of lime, not 55 grams of lime. So how do I get 55 grams of lime if I have a recipe for 21 grams of lime? Okay, let's say that you have a recipe for 1 dozen cupcakes, and you are told to make 30 of them. What would you do? To make exactly 30 and have them turn out just like Grandma made them.
Come up with a proportion.
Proportions for what? I'm going to make, think of it this way, how many batches are you going to make? If I make 1 batch, I have 12.
2, 8.
Well, if I make 1 batch, I have 12. If I have 2, I have 24. If I have 3, I have 36. I was told to make 30, right? So 2.5 batches. If I make 2.5 batches, it'll be the perfect recipe. If I take 2.5 times my ingredients, I'll get 2.5 times my products. Okay? Does that make sense to everyone? If I'm supposed to make 24, I doubled it. If I'm supposed to make 36, I tripled it. If I'm supposed to make 30, I 2.5 times it. The trick here is to figure out what multiple. How many batches are we going to have to make of this recipe? If I was asked to make 21 grams of lime, I would say, okay, give me 15 grams of calcium and 6 grams of oxygen. I'm good to go. They say, okay, but no, you're not going to make 21. You need to make 55. Okay, how many batches do I need to make? I need 55 grams. So what we do is we take how many we need to make and divide it by how many we can make with the recipe we have. If I need to make 36 and I have a recipe for 12, I take 2.5 batches. 30 is what I'm making. I have a recipe for 12. 30 divided by 12 is 2.5. In this case, I have a recipe that makes 21 grams of lime. I'm asked to make 55 grams of lime. How many batches do I have to make? 2.6 batches. And that multiplier, notice it has no units. It's unitless. Now, we've said before that numbers have no meaning unless they have a unit, unless it's derived. And the derived unit is grams divided by grams, which is nothing. They cancel each other out. So it's a multiple. It's a multiplier. I have a multiplier of 2.6. If I have a perfect recipe for 21, I can make 55 if I make 2.6 batches. And so what I'm going to do is go through and take my perfect recipe and my multiplier of 2.6 and multiply everything by 2.6. 2.6 times this plus 2.6 times this produces 2.6 times this, which is what we were asked for. That's how we came up with it. So I'm going to make a recipe according to this perfect, or excuse me, a batch according to this perfect recipe. 3 times is here. 2.6 times this is 39 grams. 2.6 times 6 gives me 16 grams, and I produce 55 grams of lime. No leftover oxygen, no leftover calcium. Why? It's a perfect match. Why? Because I had a recipe for a perfect match to make 21, and I made 2.6 batches of it. Because the law of definite proportion says if you have them in the right proportion, they will produce the correct product. We have a few minutes left, right? 6 minutes? Why don't you go ahead and try to attack on your own 2.5, and we will go over it together in just a few minutes. On your own 2.5, you have a mass of carbon and a mass of hydrogen to produce natural gas. Don't worry about the formula for that right now. There's no leftover carbon or hydrogen when you use that much. So how much would you need of each to produce 128.4 grams? I mean, the fact that there's nothing left over tells you what? That this is a perfect recipe, right? So you should have already figured out that the perfect recipe here, 24 grams of carbon and 8.08 grams of hydrogen, is going to produce 32.1 grams of natural gas. Because you all remember that addition and subtraction is precision, and you can only have an answer that's as precise as your least precise, which is to the tenths place, not to the hundredths place. Right? That's why it's 32.1, not 32.08. So what we have on the board now, 24 grams of carbon, 8.08 grams of hydrogen. That's the perfect recipe to produce 32.1 grams of natural gas. Right? So if I asked you to produce 32.1 grams of natural gas, you could do it without doing any conversions. Say, yeah, I need 24 grams of carbon, give me 8.08 grams of hydrogen, poof, I'll make natural gas. Actually, you make natural gas and then it goes poof. But anyway, make natural gas and no leftovers. Perfect. You know, when I take it out of Easy Bake, there's no hydrogen, there's no carbon left over. It's all turned into natural gas. But you weren't asked to make 32.1 grams of natural gas. You were asked to make 128.4 grams of natural gas. So my X factor, my multiplier, 128.4 grams, that's what I need to make, divided by, I have a recipe that perfectly makes 32.1. So I need 4.00, because each one of those, it's 4 sig figs divided by 3 sig figs means I need 3 sig figs, right? 4 times. It's a 4-time multiplier. I take my perfect recipe to make 32.1, and I make 4 batches of that. So 4 times 24.0 plus 4 times 8.08 produces 128.4, or, doing the math, 96.0 grams of carbon plus 32.3 grams of hydrogen produces 128.4 grams of natural gas. But note, make a note of this in the answer key too. What is 96.0 plus 32.3? $128.3. But this is right. You got to be savvy enough to know that my answers might be off a little bit because of the rounding that I have to do in order to maintain appropriate sig figs. This is the correct answer. If I asked you, if you combine 96.0 grams of carbon and 32.3 grams of hydrogen, it'll produce how much natural gas? And you came back and said 98.3, that would be right. But because we started with this is how much we're going to make, and we came up with a multiplier, you apply the multiplier, and you know that within this there's some rounding. And so this is correct for the way we work this problem.